Another tool that we can use is looking at the orders of magnitude in something and this thing that we call Fermi calculations in physics. And these are ways to quickly check your results to see if they are reasonably correct or if they make sense. So first, orders of magnitude. How many powers of 10 something has? And this is using scientific notation. I'm not going to talk about scientific notation here. I'm going to assume in this video you already understand it. You've already gone over it. If you haven't, or if you're unfamiliar, or if you're uncomfortable with scientific notation, it is absolutely critical that you talk to me in class. If I don't hear from anyone, I'm going to assume that you understand scientific notation. If you're just feeling weak with it, let me know and we can go over it. But for now, we're going to assume that kind of everyone understands it. If you need help, pause, get a primer with me before you go on in this video. So we can use scientific notation to easily compare values, because if I look at this and I look at this, I know that these two numbers differ by 10 to the second. I know that this one is 100 times bigger, or it's 10 to the second times bigger. And orders of magnitude are useful because when we're doing calculations in physics, especially when you get to more advanced physics, you can often get off by massive amounts that make it really easy to say, like, there's no way that this number is right, just by looking at how big or how small it is. Whoops. And then Fermi calculations are about estimating the order of magnitude of an answer. Okay, so as an example here, a story that was told to me by my physics teacher was he often had students do some of these quick calculations on an early test. And the goal was to just get you to sense, do you have an idea of what's reasonable or what's not? And so one student, he said, like, estimate how much paint it requires to paint a deck, or, you know, to paint an area. And a student said, you know, 15 million liters, or like 1.5 times 10 to the 6th liters of paint. And so you can just imagine, right, like, if you've ever painted a deck before, or even painted a room or a wall, you know that you get like a couple cans and that should be good. And then if you imagine, you know, bottles of soda and say, like, okay, if each of those bottles of soda is a liter, maybe a can is 4 or 5 liters if it's a really big can, but there's no way that we need millions of liters of paint to paint the deck. He also talked about sometimes where he would ask students to estimate or calculate the distance between the Earth and the Sun, and someone came up with, you know, something like 100 meters. And it's like, clearly, we're nowhere near the right number. Even if you don't know what the number is, you know it should be, you know, millions or billions or trillions or bigger, the distance between the, you know, the Earth and the Sun. It's not hundreds of meters. That's what we're talking about with order of magnitude. Fermi calculations is this idea of how do you do an estimation quickly just to get, you know, am I looking at tens, hundreds, thousands, millions, etc. So let's do a quick example. How many steps to the top of the IGA building? And the idea behind a Fermi calculation is to just get rough estimates of the numbers and get a ballpark. So if I'm thinking about it, I'm imagining, you know, each of those landings. I'm guessing there's about 10 steps per landing, between landing. You know, it's about right. It's, you know, it might be 12, it might be 11, it might be 9, it might be as low as 5 or as high as 20. But, you know, it's definitely right around 10. I'm picking 10 because it's an easy number to work with. And then if I think about it, there's 2 landings per floor. And then if I think about it, there's 6 floors in IGA, right? There's ground up to the 6. So actually, we could say that there are 7 floors. Let me fix that. So if we look at this, I'll also do some dimensional analysis here. 10 steps per landing. 2 landings per floor. And 7 floors. And then if we look, floors will cancel with floors, landings will cancel with landings. We're left with just steps. That's a good sign. That's what we're trying to solve for. And we will get 140 steps. So we're saying it's about 140. Honestly, we could even do this more simplified if you weren't trying to think. We could just say that there's about 10 steps between floors. Let's just say roughly there's 10 steps between floors, and there's about 10 floors. So there should be about 100 steps. The goal here is not to get a super precise answer or a super accurate answer. It's just getting the ballpark. But you see, even though these numbers were different, they are close. They're both in the hundreds. So if someone said, oh, it's actually 200, you'd think, okay, yeah, that seems reasonable. Or if they said, oh, it's 150, you'd be like, okay, that's reasonable. It's 90, that's reasonable. It's close to 100. If someone, however, came and said, oh, it's 2,000, that's a whole order of magnitude. That's 10 times more than you estimated. You're probably not off by 10 times. Or if they said there's 10, you're probably not off by a factor of 10. Now, when you start getting to bigger or smaller numbers, you might say, okay, as long as I'm within plus or minus, 2 orders of magnitude, that's good enough. But the idea behind a Fermi calculation is just doing some quick estimates, even if they're just, is it 1, 10, 100, 1,000, 1/10, just picking powers of 10, multiplying things up and estimating. Oh, that's our next video, so I will stop here.